Okay, in this video, we're going to continue assignment number 10 from my Calc CD class. We are doing a lot of line integrals, and we are trying really hard to distinguish between vector and scalar line integrals. That's what we really got to make sure we're doing right, because that kind of determines everything you do. So here we have f of x, y, z, scalar function. That's the first thing you got to notice. And then is x, y plus z. We have r of t is cosine of t, sine of t, t. That's the same as the previous problem, and then we're going from 0 to pi. So since it's the same as the previous problem, I'm going to steal the work from that. I'm also going to assume that you watched it. I will go back, when the time comes so that we can see what I'm stealing. But first up, find f of r of t. So f of r of t for this scalar function is going to be x is cosine, y is sine, so cosine sine, and then z is just t. So cosine t, sine t, plus t. And then that doesn't really simplify, although I do think I'm going to do something when we integrate this thing. Now, the relevance of this being the same as the previous one is that ds, which is the magnitude of r prime of t dt, we found in the previous problem was just root 2 and then dt. The reason for that is that you're doing the square root of negative sine squared plus cosine squared plus 1. And sine squared plus cosine squared is 1, so that's 1 plus 1 is 2, square root of 2. That's where that came from. All right, so now we want to set this up. So we're doing the integral along the path of f of xyz ds. T goes from 0 to pi. So we'll just plug those in. F of r of t is, so it's cosine t, sine t, plus t. And then ds is just root 2 dt. What I'm going to do here, because I think it's a little bit easier, is I'm going to use the double angle formula for sine. Sine of 2t is 2 sine t cosine t, which means that sine times cosine is 1/2 sine of 2t. And this comes up a lot when you're doing polar, mostly when you're doing polar, or powers of trig functions. So I'm just very comfortable doing it. So I'm going to make that substitution and change my integral. Change the integrand, basically. You don't have to do that. You could just let u equal cosine or let u equal sine. You will get the same result, but I like to do this. All right, antiderivatives. You get root 2, quantity negative 1/4 cosine of 2t plus 1/2 t squared. We're going from 0 to pi. When we plug in pi, we get the cosine of 2 pi is 1, so you get negative 1/4 times 1, and then pi squared over 2. The cosine of 0 is 1, and then, t is 0. So we get this. This cleans up ultimately to square root of 2 over 2 pi squared. So this was a scalar function, and that triggers all the things that we know that we have to do. Let's look at the next one. We got a vector field. So f is x, y, z, x comma y comma z. R of t is cosine sine t, which again is the same, I think, as the previous one. But because this is a vector field and not a scalar function, it doesn't matter. It doesn't help us to know that in this case. And then we're going from 0 to pi. So this is a vector field. So we're going to do f of r of t and then calculate dr, which is r prime of t dt. Can't stress it enough. That's the thing. You have to just identify what you're dealing with. And from there, it's just crazy substitution problem where you have to know what to substitute. So we need to find f of r of t. We got our x, y, and z. So this is a straight substitution. Cosine, comma, sine, comma, t. dr. So remember, for dr, you have to go back to r of t. So the derivative of cosine. So this one's a little deceptive, though, because r of t is basically f of r of t. But we're going back to r of t. We're not looking at f of r of t. So this will be the derivative of cosine is negative sine. The derivative of sine is cosine. And the derivative of t is 1. And then there's a dt, because we're going to need that differential. What are we integrating with respect to? So the line integral along C of f dot dr is going to be the integral from 0 to pi. And then it's f dot dr. So we take f of r of t dot dr, which we found is negative sine of t cosine of t 1. We actually do the dot product. In this case, we get negative sine cosine plus sine cosine plus t. So all that's left is t. So we will get this, reverse the power rule, plug in, you get pi squared over 2. Not a bad problem. All right, let's take a look at the next one. F, so vector field, xy, comma 2, comma z cubed. R of t seems to always be cosine sine t. I don't know. And then we're going from 0 to pi again. So f of r of t is going to be cosine sine comma 2 comma t cubed, just by substitution. dr is magnitude of r prime. No, it isn't. ds is the magnitude of r prime of t dt. dr is r prime of t dt. So you can't really confuse them because you're going to have to do a dot product with f of r of t. And if you've like accidentally calculated ds, how are you doing that dot product, right? So once you kind of got it all down, like you can do what I did where you just lose sight of what you're doing. But then when it all comes together, you wouldn't be able to really do that integral in a meaningful way. So you don't have to worry about that once you've locked it in your brain of what to do. Prior to locking it in your brain, it seems like there's a million different options. There's actually not. There's basically just two options. So we got to find r prime of t, going back to r. So the derivative of cosine is negative sine. The derivative of sine is cosine. The derivative of t is 1. And then there's a dt. All right, so the line integral along c of f dot dr is going to be do the actual dot product. I'm just going to like start doing them, right? So the dot product here is going to be cosine sine times negative sine, which is negative. So we're doing the integral from 0 to pi. You get negative cosine sine squared, and then you'll get 2 cosine, and then you'll get t cubed. So doing the dot product. So, you know, as you get more comfortable, there's like, you can get away with showing a lot less work, I guess, is basically what I'm saying. We need to integrate all of this. I'm going to assume you can and just do it. Negative 1/3 sine cubed plus 2 sine plus 1/4 t to the 4th from 0 to pi. Plug in pi. The sine of pi is 0, so almost everything goes away. The sine of 0 is also 0, so almost everything goes, actually everything goes away there. So all we're left with is going to be pi to the 4th over 4. That's the only thing that we're left with. Everything else just zeroes out, which is kind of the best. So that's our answer. All right. Let's take a look at another one. This will be number 15. F of xyz is 2x squared plus 8z. We notice immediately that is a scalar. So we know we're doing f of r of t ds. So we have to find f of r of t, and then we have to find ds, which is the magnitude of r prime of t dt, set up our integral, and do it. All right, so we got f of r of t. We can again identify x, y, and z. I do think it's kind of helpful to visually identify them, but like it doesn't change, so you don't really need to do it. So this will give us 2e to the 2t plus 8t. So y is not actually involved in f of x, y, z, which is, I don't know, good maybe. We need to find ds. So ds, magnitude of r prime of t dt. So that is going to be the square root of the derivative of e to the t is e to the t, so e to the t squared, plus 2t squared plus 1 squared, and then dt. Okay, so we are doing the integral along c, or over c, of f ds. So f we have is 2e to the 2t plus 8t. We're going from 0 to 1, 2e to the 2t plus 8t. ds, I think we should simplify here. It's e to the 2t plus 4t squared plus 1 dt. This works out to be a perfect u substitution, right? If we let u be this, then du is going to be 2e to the 2t plus 8t, which is exactly what we have sitting out there. So this is just u to the 1/2, so plus 1 times the reciprocal will give us 2/3 u to the 3/2. And since we're staying with t's, we're going from 0 to 1. Plug in 1, plug in 0, we get this, and then this doesn't really clean up, so I'm going to leave this as my answer. That by doesn't really clean up, I mean that does not clean up at all. All right, let's look at 16. F of xyz, scalar function, is going to be 6xz minus 2y squared. R of t is t squared over root 2, t cubed over 3, and we're going from 0 to 2. We have to find f of r of t, which I think I have accidentally written as f of xyz. It's not f of xyz, it's just that x, y, and z are going to be t squared over root 2, and t cubed over 3. I should have written f of r of t. I don't know, I'm not going to change it. So it's going to be 6 t and then t cubed over 3 minus 2, and then t squared over root 2, quantity squared. This will simplify quite a bit, right? Because this is basically 2t to the fourth and then minus t to the fourth, which is great because that means it's just t to the fourth. So f of r of t is t to the fourth. And again, I should have written f of r of t. We need to calculate ds, which is the magnitude of r prime of t, dt. So this will be the square root of, the derivative of t is 1, so squared, plus the derivative of t squared over root 2 is 2 over root 2 t. And then we're going to square that. And then the derivative of t cubed over 3 is t squared, so plus t squared squared. All that dt. And then that's going to simplify down a bit. So we're doing the integral over c of f ds. You can see I'm starting to make some mistakes in my writing here. It's getting a little sloppy. I don't like to see that, but there are so many problems in this problem set, so I don't really blame myself, and I don't really blame you if it gets a little sloppy. We're going from 0 to 2, because those are bounds. F of r of t, which is t to the fourth. And then this square root thing actually just simplifies to 1 plus 2t squared plus t to the fourth. And you can work that out. You end up with like 4 over 2 when you square 2 over root 2, which is 2, and then t squared, and then t to the fourth. dt. All right, so now you have to hope something good is happening here, because otherwise what are you going to do? So I noticed that 1 plus 2t squared plus t to the fourth actually factors. So this factors into the quantity 1 plus t squared squared. And since t is between 0 and 2, that's always positive. So we don't have to put an absolute value. We can just pull that out as 1 plus t squared. So we're really just doing 0 to 2, t to the fourth, 1 plus t squared, and then dt. All right, so distribute, reverse the power rule, use the fundamental theorem. We get this. This you could, I think you could probably leave this, but I did some more math and I ended up getting whatever that is. 864 over 35 was like my final answer there. All right, let's look at another one. So many of these. It did say at the beginning of the first one, we are just doing tons. Okay, this one's a little weird. We're doing the integral over c of 1 ds, right? So we're basically just finding arc length here. R of t is 4t minus 3t and 12t, and then 2 to 5. So all we need to do is calculate ds. F of r of t in this case is still just 1 because I guess f of xyz is a constant. It's just constantly 1. So we just need to find ds, which is the magnitude of r prime of t dt. So that'll be a square root, and then you get 4 squared plus negative 3 squared plus 12 squared. Close that off in a dt. This gives you square root of 169 dt, and then square root of 169 is 13. So 13 dt. Great. So we want to do this. We're going from 2 to 5. It's just 13 dt. I mean, it's 1 times 13 dt, but whatever. Integrate that, and you get 13t from 2 to 5, which is going to be 13 times 3, which is going to be 39. And as I said, this just represents arc length in this case. So sometimes you will get, line integrals that represent certain things, physical things, things from physics. In this case, arc length. Looks like the next one will also be arc length, and also the last one in this video. So let's do it. The integral along c of 1 ds. So again, we're just finding arc length. Because if you think about it, like ds is the magnitude of r prime of t dt. That's exactly arc length from like calc 2, I guess. So r of t is e to the t root 2t e to the negative t, and we're going from 0 to 2. So again, just calculate ds because f of r of t is 1. So ds is the magnitude of r prime of t dt, square root of derivative of e to the t is e to the t. The derivative of root 2t is root 2. And the derivative of e to the negative t is negative e to the negative t. Whew. dt. Okay, so this, I don't know, cleans up, or at least you can rewrite it. E to the 2t plus 2, and then plus e to the negative 2t. And then this takes a special observation, in my opinion. This is just e to the quantity e to the t plus e to the negative t squared, and then dt. I think that's a special observation. If you're doing these consecutively, And on the previous one, you also would have kind of run into something like that. So like maybe that helps it make more sense. But otherwise, you're like, what am I going to do with this thing? So here, again, we get just e to the t plus e to the negative t, and then dt. Again, we don't need absolute value because e to the t plus e to the negative t is always positive. So, you're not going to run into a negative there. All right, so our line integral that we're doing is just going to be the integral from 0 to 2 of ds, right? So e to the t plus e to the negative t dt. Integrate both of these, you get e to the t minus e to the negative t, and then from 0 to 2. And then we plug in 2, we plug in 0. Our final answer is e squared minus e to the negative second. All right, that's it for this part of the problem set. I will be back in the next video to continue with it. I hope this was helpful, and good luck.